Hi, so can you see my screen? Can you see my screen? Anybody?
Yes, sir.
Okay. So just first of all,
Sir,
couple of
your voice is coming very low.
so is it better now?
Yes, sir.
Oh, okay, okay. So first of all, there are a couple of things. So basically, so today is like 21st. Like 21st. Okay, so first, just couple of things that I have said before as well. So, if somehow the internet gets disconnected, I'll somehow join by some other connection, and maybe that will take a few minutes. And also, before directly delving into problem solving, so I just want to cover. Rather, I would like to point you out to two small things that I think is kind of that would be helpful. So and I also have something to say, like in the so I had taken two classes before that. So in the last class I told you people to tell me some play time of this a tutorial, but nobody actually has replied to that. So I was not sure if anybody is actually interested or not. So but anyhow, I somehow scheduled a meeting after talking to Saurabh, and then so the point I want to make is, like, if you people have any problem or doubts and something, then you people should feel free to ask us. I mean, there is no point of not saying anything, because we cannot understand what is going on unless you people say us to any of the TAs or to sort of, I think, unless you people say us, we cannot really help you. I mean, so and hopefully, I don't know, but I request you to, like, clear your doubts, and first of all, most importantly, and you people to some sort of clear your basics of this. I mean, it may be the case, like, you may not be able to solve some particular problem or something, but I mean, that's okay. But I mean, everybody cannot solve everything. So but it would be important to clear your basics, and if there is any doubt regarding the basics material, I think it's time, like, you should revisit that thing. So and yeah, and if you people need more tutorials, I mean, we are happy to help. But unless you let us know, we cannot I mean, we don't know what is going on, right? I mean, where you are struggling or not. And since this is an online course, I mean, it's kind of difficult already. It's kind of difficult for both the students as well as the teachers. Okay, so enough of this sort. So am I
Hello.
audible?
Yes, you are audible.
Okay, okay. And also, just one more thing there, as I've said before, I mean, don't call me sir. I mean, that should be the last thing.
Hello. Hello.
Yeah.
I have some doubt.
Yeah, yeah, just moving,
Can you?
just directly delving to your doubts. Let's just like let me just cover I think two or three things, and then we'll directly jump to your doubts. All right, that sounds okay.
Okay. Okay.
So so do you people remember what a dearrangement is, right?
Yes.
Has sort of covered it, or you know by yourself? Hello.
Yeah, we have the sir has mentioned it and discussed it in class, but we haven't done the recurrence relation and the proof of recurrence relation.
But has sort of actually I mean, solved the problem, like, not via recurrence, by directly inclusion exclusion or something.
I don't think so. He just mentioned, and he said that he'll take some examples in later.
Okay. He probably told you people to check it out. So I just want to cover that first then, and it's kind of a very beautiful thing, I would rather say. And so suppose there is a math club, or suppose there is a DMath club in a town, and obviously the club holds meeting after periodic intervals. So during a meeting, so there are n persons from 1 to n, and each person has a hat. So like hats are also numbered from 1 to n. For simplicity, let's assume that person 1 has hat 1. Okay. Similarly, person 2 has hat 2, and person n has hat n. Okay. Now suppose before like directly going to the meeting, they somehow keep their hats aside in a place before entering the meeting room, and the idea is like after the meeting ends they will come and get their hats. Okay. So now we understand kind of a pretty interesting question. So the question is like, how many ways so the question is like so somehow so basically the point I want to make is like, how many ways are there so that nobody gets their own hat. Okay. So everybody somehow gets someone else's hat. So let's try to find the recurrence, and then let's see how we solve this. Uh, Let us assume like dn is the number of ways. Okay. So any idea? Anybody? Anything that you might you think it may work or something? I mean anything at all? I mean, just take a guess. I mean, it doesn't have to be right. I mean, anybody? Hello, am I audible? Is the connection one lost? Hello. Hello, am I audible? Ja. Hello, am I
Yes,
audible?
you are audible. You are audible.
Oh, okay. So just somebody please, I mean, reply. I mean, I really don't understand whether my connection has gone lost, or whether, I mean, nobody's.
Actually, we know the recurrence formula, but we need some time to discover.
Okay. So what is the recurrence formula? Maybe.
That is n minus 1 into dn minus 1 plus tn minus 2.
N minus 1 into.
Tn minus 1 plus dn minus 2.
So any idea how does that work? So,
That is not clear.
so anybody wants to take a guess or something?
We can select one person, let's say ith person, and we know that since it is a de-arrangement, ith person cannot get his ith hat.
Right.
So we assume that, let's assume the first person is there, and first person's hat is with the ith person. Then the problem is basically you have to arrange the remaining n minus 1 hats amongst the n minus 1 people, which is dn minus 1, or if the hat of the ith person is with the first person, then we only we have to
Yeah.
arrange
Yeah.
dn minus 2.
Yeah. So you're correct. So does anybody follow what what he has been saying, or shall I explain it to you like more rigorously?
So please explain.
Okay, don't call me sir. Okay, it is a request. So let's assume, let's consider our problem. Let's say, let's make our problem more structured. So let's assume that, say, person one doesn't, so we know it is a D arrangement, right? So person one doesn't get his own head. So let's assume person one gets hat I, and we have assumed this identity mapping of these persons with their heads. So person was had actually had one, but somebody else has got that, and some person one has actually got person I's hat. Okay, so now there are two cases that can happen, right? So there are two cases. So one case is like person I gets person one's hat, right? One possible is like, so let me just write it and I'll explain it to you. So let's assume this is person one, okay, so P1, and this is like hat one. Now we know somehow there is a connection like that, right? And that actually belongs to, so let's make it a little bit more see to follow. Let's assume for every point we are assigning a two tuple, so person one and hat one. Similarly, person I, hat I, right? Now, what according to our this assumption, so we are assuming that person one gets person I's hat, right? Now, what happens to that person? So let's assume this is the direction. So what happens to the person I? So one possible thing is like, one way to do it, like one possible way is to like person I also gets person one's hat. So it's kind of a loop of length 2. Or say person I actually gets the hat of some person J, right? These are perfectly valid idea, right? Valid condition, right? Hello,
Yes.
right? So suppose let us first think this case, okay, and we'll consider that case as well. So you know that in this case person I doesn't gets hat 1, so this should be hat 1. No, in that case there are n minus 1 other persons and n minus 1 other hats, right? That are like same D arrangement, like nobody gets their own hats. So right, this actually becomes like dn minus 1, right? And there are so there is nothing great about this hat I. So person 1 can get any hat other than his own hat 1. So there are n minus 1 choices of that, right? Is this part okay?
Yes. Now it is clear.
Anybody anybody else who has some doubt regarding it? Maybe we can cover it, maybe we can go through the argument once more. Anybody? I mean, feel free to ask. I mean, if you have doubt, just ask. So the idea is like person one gets hat I not equal to one, right? And like so there are two cases that can happen. I gets person one gets person i's hat, but person I can actually get person one's hat or some other one's hat, right? So let us first consider this case. Okay, this is the calculation here. So we can somehow assign person I to the person one's hat, right? And assume that so person one is like getting hat I. Now, now suppose let's do a thought experiment and assume that I should get hat one, right? But that is not the case here. So here we are considering person I doesn't get hat one, right? So there are n minus one person remaining, and there are n minus one hats remaining, and nobody gets their own hat. And this can be done in dn minus two, dn minus one ways. And there is nothing special about hat I mean, person one can get any hat other than his own hat, and that can happen in n minus one ways, right? Right. So there is nothing special about this I. There is nothing special about this I, right? So there are so in this case, for this case, there are like I'm still not very comfortable using it. So let's just yeah. So anybody who actually now wants to think, say something, say his or her thoughts about this case? Anybody? Hello, hello. Yeah,
This one will be n minus 1 into d n minus 2.
yeah. So basically, as I have drawn it here, so like P1 is getting hat I, and here we are assuming like Pi hit is getting hat 1. So there are n minus 2 persons, and there are n minus 2 hats, right? And this can be done in n minus 2 ways. But note that there is nothing special about this I. So there is, so you can actually choose n minus 1 way about this person one set. So basically, actually, this becomes like dn of n minus 1 into, right? So this is the recurrence, right? Is it clear, or shall I go through once more? Hello, hello.
Clear for me.
Okay, okay. So now the idea is a little bit of algebraic manipulation. So one possible way is like subtract n minus 1 into dn minus 1 from both sides. So it will be something like dn minus n into dn minus 1, and similarly n minus 1 dn minus 1 plus minus 1 dn minus 2 minus. And so if you assume that an is like defined as dn minus n into dn minus 1, then after doing a little bit of algebraic manipulations, you can actually show like dn minus n into d of n minus 1 would be like something like minus 1 to the power n. So like dn would be like minus 1 to the power n plus n dn minus 1, right? Right, and like if you see carefully like these base conditions, so d0 would be 1 and d1 would be 0, and like if you want to solve this thing like a recurrence kind of thing, so it can actually turn out to be something like something like this form. So n equal to 0 to infinity dn n factorial x to the power n, and if you like so it will be something like 1 plus. So if you work it out by your hand, I mean I have done this in my hand, so by my hand, so if you people also work it out by your hand, and then maybe this thing will be far more clear. And maybe if you have still more doubts, then maybe we can actually discuss it then. So if it will be something like this form, and then if you actually like move it around, and then we'll somehow get something like that. So something like d of n is, so let's assume like d of x is like x d of x plus like e to the power minus x, and then it will be like d of x equals to e to the power minus x by 1 minus x, right? Something like that. So it will be like e to the power minus x into 1 plus x square. So this will be something. I mean, it's pretty hard to calculate it by hand. So I mean, it's better that you people do it by your hand, and then maybe if you face any difficulty, then maybe we can actually have a look at that. That's okay.
Hello.
Yeah.
Why d0 is equals to 1 and d1 is equals to 0?
D0 is 1, D1 should be 0, right? Because there is a single person, a single hat, and there is no other way to get that person his her some wrong hat, right? There is only one person and one hat, right? There is no way of like make a mistake there, right? There is only one hat and there is a single person. So suppose that person goes alone in the club, right? There is a single
That
hat.
this I understood, but why d0 why this is 1?
Zero is basically one is like there is, see in this case actually basically there are 0 persons, right? That doesn't actually really make sense per se. But in order to go this recurrence, like in order to make this recurrence make sense, I mean let's say assume this d0 is 1, right?
So
But
we
that
can
doesn't,
assume like d1 is equals to 0 and d2 is equals to 1.
yeah, you can do that.
Okay.
I mean see now, so let's just compute it by our hand. So there is nothing wrong. So what happens with d2? D2 would be like minus 1 to the power 2 plus 2 into d1, right? So it will be 1 plus 2 into 0, right? This is 1, right? And the reason being there are person 1 with hat 1 and person 2 with hat 2, right? Now, the only possible way for each of them to have a rearrangement is to take each other's hat, right? There will be a kind of a loop kind of thing, right? I mean, if we assume this, so if we assume d1 equal to d0 equal to 1, then we can actually have d1 is like minus 1 to the power 1 plus like 1 into d0. So in order to make that sense, in order to make that 0, we need d0 equal to 1, right? But as you have said, like using different base conditions, actually they are kind of equivalent here, right? Hello?
Yes, sir.
Yeah. Okay. Okay, and so I just request you guys to uh, just check this out by yourself. I mean, just try to do this part by your hand, and if you cannot, if you face any problem, maybe we'll discuss that. That's okay. Hello. Hello. Hello.
Sir, you're audible.
Yeah. So just somebody please reply. I mean, I'm really not understanding. I mean, what is going on? And also there is a small thing that I want to discuss. So just give me a moment. Yeah. So do you people know this Master's theorem, divide and conquer? Hello. Do you know Master's theorem?
No, sir. No.
So it's kind of a tool for like checking recurrence solutions. So note that this is a tool for checking. This is by no means a way to prove it. Okay. So let me just write the statement and then I'll discuss. So suppose Tn is like, some noise in the background. Sorry about that. Is there anybody who has actually seen this thing? Anybody?
Yes.
Yeah.
Yes.
Okay, okay, good. So basically, for the people who have not seen it, so basically, it's something called divide and conquer. Uh, so this is a technique of algorithm, and so the idea is like, suppose we have a problem of size n. So there is a problem of size n, and suppose we have broken it into couple of problems of like small sub problems of size n by b, and total number of them is like a, right? 1 2 dot dot dot, this is a. And during this division computation, during this breaking this whole thing into these sub problems, let's assume that we have done say theta of n to the power k log n to the power p extra work, right? So basically, given a problem of size n, we have actually reduced that problem into small problems of small sizes. And the idea is like, then again we'll like divide this thing, and eventually we'll get to a problem of size very small, say 1 or 2, and in that case we can like brute force we can solve it, like. So this is kind of the idea of this divide and conquer. So basically the idea is like, solve these smaller problems, and then work all the way up, and then get the solution to the original problem. So this is kind of the idea. So the idea is like this. So suppose we have something, say Tn, and we have broken it into size of n by b, and so by default size of n by b, uh, problem size of n by b takes t of n by b, and there are a many such copies, so 1 to a. And suppose the extra work we have done is like theta of n to the power k. Then based upon these various conditions of a and b and relation to t, basically we can actually directly obtain uh, a solution of Tn. So now the point is like, the point I want to make is that this is actually for checking. Like, so suppose you are given a recurrence relation, or somehow you are designing an algorithm and you have come some sort of a recurrence relation like this, and then basically you can actually check whether what will be the running time or solution to your recurrence using this. And the point I have to make is like, this is a super big thing, and don't try to remember it, and just like know some that there exists something, and whenever you need it, you probably use it. And also another point I want to make is like, this is a tool for checking. This is by no means a solution. So if you want to solve a say recurrence relation, you have to some sort of either guess or go via generating function or any other kind of technique. And given that technique, you can actually check your solution using this. Okay. So there are a couple of versions of this master theorem. So there is a version in CLRS that is, that looks slightly different than this version, but they are obviously equivalent. And actually, I like this version more. So maybe, yeah, that's why I'm showing you that. So this is a tool. Also, the one point I want to make is like, say in some cases, like suppose like Tn is 64, say Tn by 8 minus say n square log n. So can you tell me what will be the answer to this thing? Anybody? Hello? Hello? Just try it out.
First one.
So you're saying this
Theta
first
into
one.
the power log. Log 64
So,
base 8.
but there is a small problem. There is a plus sign here, plus sign there, and a minus sign here. So we cannot directly apply this thing, right? So what does this recurrence actually mean? This actually means like we have divided this nth instance problem of nth instance, instance of the problem of size n into problems of size n by 8, and there are 64 among them, but we are actually somehow subtracting. But here the idea was like we are doing some additional work during this division kind of thing, breaking it up into problems, this divide section, right? So unfortunately, so this doesn't work. Master's theorem does not work. So the point I want to make is like, although this is a very nice and useful tool, but this does not actually covers all cases. Like this is a valid recurrence relation, right? Just the fact that it doesn't follow here doesn't mean it has no solution. It certainly has a solution, but we cannot actually directly find it using this formula, right? Also, there are a couple of like formulas that are not kind of this division kind of thing. So given a problem, we are breaking up into smaller subproblems, right? So there may be other forms of recurrences, not divide and conquer. So in that case, this divide and conquer doesn't work as well. So there is a slightly more advanced version of master
Ask
theorem.
something.
This is something called Akra-Bazdi method, but you can actually look it up in Wikipedia. But even then, that doesn't cover all possible cases. So basically, there is no actual substitute for our good old guessing and solving. Like, okay, so there is that. Yeah. So now we have actually come.
Uh,
Yeah.
I wanted to ask something.
Yeah.
Sir, for the cases where it will not be applicable, that is okay, I understand. But for the cases where it will be applicable, there why can't we use it as a solution? Because it is a theorem.
Yeah, but you are actually so this is direct plugging formula, right? So the idea is like you can actually verify it by this, but you have actually like kind of solve this. Say let's assume this. Let's see a solution. Let's see an example. So like
So what's up? Couldn't hear.
okay, so so the point I am to make is like this is a just a verification tool, as I've said. Like since this is a not a universal theorem, so basically it's actually a good idea to actually keep solving things. And so basically this is a not a this is a only verification tool. So if you are given a problem in your problem set or exam, so you can verify it using Master's theorem, but just directly writing out the solution won't work. I mean, you won't get marks. Okay, because that's not actually our goal, right? Our goal is to learn this process, and since this is not actually a universal theorem, so it's not at all a good idea to just rely on that only on this theorem. Okay, so if you use this, like it will be something like order of n square. If you use it should be like theta of n square, I think. So a is 3, b is 2, and k is 2. So yeah, 3 is, so it should be like case 3a, and like this will be the case. So basically, yeah, but when you actually have to solve this, so basically you can assume like tn is equal less than equal to some cn square, and then we actually have to plug like t of n equal to this 3c into n by 2 square. I mean, yeah, I mean you understand, right, the point, right? So and this plus n square, right? So it will be something like what is Tn by 2? So Tn by 2 would be 3 into T of n by 4 plus like n by 2 square. And you can directly plug it here and then solve it and actually verify it is n square, right? So this will be so just for practice, maybe you can check this out. Yeah. Okay, so this is not a valid solution to our course. I mean, this is not actually universal theorem, and it's not at all I mean, good idea to just rely on this. Yeah. So these are two
But we
things.
can guess the solution using Master's theorem and
Yeah,
then
yeah,
prove
yeah.
it
That's
by
perfectly valid. That's perfectly valid. But you have to be careful with this proof, right? I mean, that's the idea, right? You want to check or guess efficiently. How do you guess efficiently? That's a possible tool. But as I have said, it doesn't cover every possible cases. So there is not a unique theorem that solves all kind of recurrences. Yeah,
after guessing we have to prove it by induction.
by induction or any way you want to prove it, but that is not a solution. That is not a solution directly using this formula. And also I just want to cover one more thing that I wanted to say. So yeah, so
So I
basically,
wanted to ask one more thing.
yeah,
So suppose for some reason we are not being able to unfold it or guess it by other means, then we can guess it by this and then prove it by induction, right?
yeah. I
So
mean,
in that case, do we have to write the whole Master's theorem or just putting the value will work?
no. So Master's theorem is in your mind, right? And like
Yes.
you suppose in this case guess T of n equal to n square. So you can directly write like
We can directly write that
write like,
T of n is
let's
equal to.
assume that Tn equal to less than equal to n square and then solve it, right?
I mean, we can directly write the guessed value and then prove.
Yeah. There is no harm in that. But that proof should be complete, mathematically sound. I
I
mean,
mean, the induction should be complete.
yeah. It should be completely sound. Okay. Okay. And I just wanted to see just one more thing that I would like to say. Maybe I'll just search and then just let's see your questions now. Yeah. So just first of all, so there is an assignment that I have been I have uploaded maybe on Wednesday. So the due date is probably 27th or 28th, right? Has everybody received that? I mean, that was posted in Classroom.
Yes, sir.
Yeah.
Yes, sir.
And yeah, don't call me sir. Yeah, just one more thing. And yesterday actually I have also uploaded a problem set, so practice problem set, right? Has anybody looked it over? I mean, it's just for practice. You don't have to submit the solutions, but to get your hands habituated with this problem solving. So yeah, maybe there are 10 or 11 problems. So is there anybody who has seen these problems? Yeah. Hello. Hello. Hello.
Yes, sir. It is. You are audible.
Yeah. Has anybody seen these problems? This practice problem set?
It is on the Classroom.
Yeah, I just posted it yesterday. Yeah. So yeah. So is there anybody who has tried any problem on that? Maybe we can discuss it. I mean, it would be better if I submit if I uploaded it before, but unfortunately, yeah. So I couldn't upload it a couple of days back. So yeah, maybe we can see it now and then try to solve. uh, just one more thing, just before going to that. So let's just see that thing. Oh, can you people see my screen? Uh, I have opened this counting thing. Can you just see my screen, or only this external thing is
To the previous page.
Oh, okay. So maybe you can. So I have opened this practice set in my computer. So maybe you can open it in your phone or laptop or desktop. Yeah. First of all, is there any doubt? First of all, yeah. So before moving to that, I think that would be most important. Is there any doubt, like regarding counting or asymptotics?
Hello.
I mean, pretty much anywhere in the course.
Hello. I have a doubt.
Yeah, yeah.
In the assignment 4,
In the
there is
assignment,
a question number second talking about the combinatorial form, writing about the combinatorial form of the sum equation.
yeah.
So what we actually what is meant to do in that question?
Okay. Okay. Just one second. Let me just explain a solution to you, and then maybe a sample solution, maybe for another problem, and then maybe it will be clear. Let's see. We have a just try to give you people a nice thing. Hmm. So let's just like see this identity. So this is actually an identity, right? Corresponding regarding this binomial coefficients, right? Hello. Hello. This is a valid identity, right?
Yes.
Yeah. So there are at least two ways to solve it. One is like doing this algebraically, like this will be like n factorial. So let's just not write it this way. This will be like n factorial by n minus k plus 1 factorial into k minus 1 factorial, plus similarly this n factorial by n minus k factorial into k factorial. And if you like algebraically manipulate it more, and then you can actually then you will actually get this left LHS, right? Now there is also, and this process is perfectly okay, but however this computations are kind of very tiresome, and then you have to be very careful regarding this calculation. So another way is like, so this is like algebraic proof. Another nice way of solving is like this combinatorial proof. Right. So can anybody guess? So how can one proceed for this like like proving it?
We can say like out of those n plus one elements,
Yeah.
we can take a specific one element.
Yeah.
And
Yeah. Yeah. Yeah.
that
Yeah. 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 You're right. Yeah. So does anybody see how she has gone to this proof? So let's write it over here once more, and then it will be feasible, I think. We try to use this. Also one thing, so if so so in general we actually, so there is a problem in this problem set, practice problem set. So basically by this box n, we basically mean from 1 to n, this set of 1 to n. Instead of writing this whole thing, we just directly write this. But this has so like no reason. So let's assume that T is a set such that, like, say T is like this box of n plus 1, right? First n plus 1 elements, right? And now suppose we want to construct a set S of say size k, right? So basically size of S should be k, right? So how many ways can we do that? So basically we will be choosing k elements from this first n plus 1 numbers, right? This can be done in n plus 1 choose k way. That actually directly gives us this left hand side. But now how would I connect combinatorially by some combinatorics to this left hand side? So let's assume that a particular element, say element I, so suppose I put element I in S, right, at the very beginning of my construction. So now there are n minus 1 n elements remaining out of this n plus 1 elements, out of this first n plus 1 element. Now note that we have already chosen a particular element I, right? So in that case, basically we will be choosing k minus 1 elements out of this, and this can be done in say n choose k minus 1 ways, right? Similarly, we can actually remove a thing, right? So we are only considering this element I. Say I either include I belongs to S or I do not include I belongs in S, right? If I if I first at the very beginning of my construction I put I in S, so there are n elements remaining, and we have to choose x k minus 1 elements only. So this can be done in n choose k minus 1 ways. And suppose I don't choose I, so now we have n elements remaining, and we have to choose k elements from them. So this can be done in n choose k. Now note that these two cases, I belongs to S and I does not belongs to S, actually covers the whole possible ways, because given any construction of S, I either choose I or not choose I, right? So this actually covers the whole space of solutions. So basically is like n choose. So basically total number of ways would be like n choose k minus 1 plus n choose k, and this actually like proves this identity, right? So this is a combinatorial way of proving instead of doing this algebraically.
So in this case, I can be any element, right?
I can be element from 1 to n plus 1. So
I think I
I
will take
actually
n
belongs to
plus
this n plus 1. Given any solution in whatever set we are constructing, I can either put I in that set or not in that set. And the important thing I want to mention here is like this actually covers all possible solutions, right? In any solution, I either put I or not put I. And if I put I in S, so there are n elements remaining and we have to choose k minus 1 among them. And if I don't put I, there are n elements remaining, but we still have to choose k elements. So this can be done in n choose k ways. Right?
I'm saying that choosing I will can be done in n plus one choose one ways.
No, no, no. Why? Because I'm just particularly selecting a particular element, right? There is no choosing for I. I'm not doing it for any arbitrary element I, right? I just say like I want to
To
take
fix the
element
element.
one, right? I'm fixing it. There is no choosing here. Is this okay?
So we have to fix the element I in this case.
No, no. So in the very first, so when you're constructing S, at the very beginning, I say like I'll take element I. So all these elements are from 1 to n, right? Right? At the very beginning of this construction of S, I just say like no, I'll just pick element I, right? Say element 5, say number 5. So once I fix number 5 and I keep it aside, right? So there are n elements remaining and then the whole thing follows.
So the combinatorial proof, we have to basically come up with a scenario in which this recurrence.
Yeah.
This
So basically, a possible solution would be like you have to write it like this way. Possible, so it's a possible solution. It doesn't have to be exactly this. So let us assume that there is a set T of this n plus 1, and we want to select a set of size k, and this can be done in two ways. When I put I in S and I don't put I in S, and this can be done in this way. And this yeah. So basically, the point I want to make is like there is an algebraic proof. Certainly, yeah, in some cases, coming up with a combinatorial proof is kind of hard. That's completely true. But like that's the beauty of it, right? I mean, these algebraic proofs can be verified, like whether it's working or not. Suppose we guess some identity and then want to check whether that identity is following, then you can do all this algebraic computation. But this algebraic computation are kind of tiresome, and there, since there are huge number of terms would be there, and maybe you can make a mistake. So another way to view it is a combinatorial. So basically in that problem, basically in problem number 2, actually you have to give some sort of
in
argument.
the practice problems, the last problems, 11th problem. So I did it with binomial theorem. So combinatorial proof. Can you show the combinatorial proof once?
So I'll just give you to think of it. I mean, just think it somehow regarding this direction. How would you choose? Like, so it is like nothing like nci into 1 to the power I and 2 to the power n minus I, right? So it will be something like, so let's just give you a small hint. So the problem number 11, practice set. So it is nothing like 1 plus nc1 2 plus nc2 4 plus like this way. So this is nothing but like sum of nci 1 to the power I 2 to the power n minus I, right? So this will be like 1 plus 2 to the power n, right? Now basically try to come up with a combinatorial argument of this state. What scenario can you think that has this? So choosing choosing the ith scenario would be some sort of like n choose I into 1 to the power I and 2 to the power n minus I. Just think of this scenario. Just think a bit more, and then I just don't want to, I mean, spoil the fun. I mean, just think a bit more, and then if you are still not okay with that, then maybe we can discuss. But just try to think of a scenario where this term is coming, like for the ith instance or something like that. The total number of solution would be n choose I 1 to the power I into 2 to the power n minus I. Just try to think of that scenario, and if you are unable to do that, maybe we can discuss it. Okay, just think a bit more. And
Actually, you were saying n choose I 2 power I 1 power n minus I.
that is okay. That is perfectly same, right? I mean, in that case, basically what you are basically doing 2 plus 1 to the power n, right? That's same, right? 3 to the power n. So basically what you are writing is like nci 2 to the power I 1 to the power n minus I, right? They are equivalent, right? I mean, the terms would be coming from 2 anyway. So basically here this power of 2 was 1. So yeah. So this is a perfectly valid. And I think, yeah, you are right. So maybe I should have written this form because it is it resembles more from that thing. Yeah, thank you. Maybe I should have written this. That actually resembles this thing for I equal to 1. Yeah. So just think a bit more, and then if you do not come with a solution, maybe we can discuss it. That sounds good.
Yes, sir.
Yeah, sure. So does anybody have any other doubt? Maybe there is a
Number 3.
pardon me.
So question number 3.
Question number 3 in which one?
What is closed form expression?
So is this problem set or assignment?
Problem set.
Okay. Yeah, basically we just have to manipulate it a bit more, right? I mean, just assume 1 to the power say something, right? N minus k. Is this okay? Right?
So question number 3.
Yeah. Question number 3 is this, right?
Question number 3 is k equal to 0 to n nck 2/3 to the power k. Find
Yeah.
closed form expression. What is closed form expression?
Closed form expression is, so let's just write it here. Right? Now, what is this happening? So this is basically a sum, right? So if we put k equal to 0, it should be like 1, right? N3 0 and 2 to the power 0. So if you put k equal to 1, so it will be like n choose 1, 2 by 3, right? And so on and so forth, right? This is a like expanded expression, right? But if you just directly see it this way, like k equal to 0 to n choose k 2 by 3 to the power k 1 to the power n minus k, right? That is perfectly fine, right? Then this actually directly follows from this binomial theorem, right? This will be like 5 by 3 to the power n, right? This is actually a closed form. So this k equal to 0. So k equal to 0 to n choose k 2 by 3 to the power k. This is basically 5 by 3 to the power n. So whatever this thing was, like this plus thing, so 1 plus this dot, this is actually a expanded expression, right? And this is a closed form, a direct formula kind of.
Sir, can you scroll up once?
Yeah, sure. This is okay, right? Or am I making some mistake? It looks okay, no? Is there any problem with this solution? I think it is okay.
No, sir, it's okay.
Just don't call me sir. Yeah, just I think this is okay, right? Yeah. Right? Hello?
Yes, it's okay.
Yeah, yeah. So do you have any other doubts? Anybody have any doubt or question regarding the material? Not only on problem set or practice set or assignment, but even for the material that I have been covering, right?
Can you just discuss a little on the assignment for question number 6?
Yeah, yeah, sure, sure. Just give me a moment. Just let me just open it and then. Problem number 6, right?
Yeah, question 6.
This safety 1, 2, and 5. Yeah.
The vending machine one.
Yeah, yeah. So where is the class where I first covered this generating function?
Yes.
This a, a similar sort of problem was there. So I've given a homework kind of thing over there. This sort of problem. So uh, so is generating function is the idea of generating function okay with you? I mean, if it is not, then let us first review this generating function and then try to move on to this problem, because
Generating function is okay. I am just worrying about the second part where it says the order of the coins matter.
Order of coin doesn't matter.
No,
Yeah,
it
yeah, order
matters.
of coin doesn't matter. Yeah, first part is doesn't matter. Yeah, yeah.
First part is okay. First part is okay. Second part is what I want to understand.
So what's the doubt? I mean, I'm still not getting it.
So like I'm trying to visualize how it changes the equations.
Oh, okay, 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 okay. Great question. So in the first part, there is no ordering matters, right? So whatever way you are putting a first 2 coins or a 5 coin, that is immaterial in the first part. But whenever there is a implicit ordering, so basically you are kind of counting it much more, right? So to submitting a coin 2 and then a coin 5 doesn't, or submitting a coin 5 and then coin 2 doesn't actually matter when in the first case, right? But when the order matters, the number would be much more, right? So once I find a 2 then a 5, because suppose I want to suppose as consider a simple case, suppose I want to pay rupees 7, right? And suppose I only have rupees 2 and rupees 5, right? And there is only possible one ways to do that, right? Using only rupees 2 and rupees 5. So let's for the moment don't think about rupees 1. So let's for the moment think only we have rupees 2 and rupees 5. So I want to pay rupees 7, and so the possible way is like I have to pick 1 2 and 1 5, right? And there is only possible one way because the order doesn't matter, right? So basically choose 1 2 coin and 1 5 coin and it's done, right? But assume the point, exactly the point when this order matters, right? Now whether you put a 2 rupees to first or second, or then so whether you put a rupees to first and then a rupees 5, or the other way around, actually gives two different solutions. So the ordering does matter. In this case the number of solution would be twice, but that's not the general. If you see like some other number and a little bit more, and then you can actually find that this is not actually double, right? I mean, there is no direct solution kind of thing, like if this is that, then it should be some constant multiple of that. It's not directly like that. I mean, there is no direct plug-in solution of that. So basically you have to compute it, right? So when the order matters, the number of solution is obviously much more. Yeah, does this answers your question? Hello?
Yeah, kind of. Okay.
Yeah, yeah. Okay. Okay, does anybody have any other doubt regarding the material event? I mean, the point I have to make is like, you may not be able to solve some particular problem, and that's okay, but you should, I mean, be comfortable with all the basics of this course, right? it's kind of a very basic course in MTech. So it's a really good idea to like clear your concepts and move on, right? And just don't hesitate of asking any doubts. I mean, we don't want to help, but unless you ask, I mean, we really don't know what is your problem, right? And then we cannot help.
Sir, what is meant by combinatorial form of an identity?
Oh,
And what is meant by that?
combinatorial form is like combinatorial proof. That should be combinatorial proof. That should not be combinatorial form. So where is that?
Combinatorial proof.
In assignment. Oh, that should be combinatorial
Yes,
proof.
sir.
Yeah. So yeah, there is a typo. That should be a combinatorial proof. Yeah, because that's already an identity, right? It's already an identity. So yeah. So does anybody have any other doubt regarding the material or some problem? Just feel free to ask. There is someone who mailed me regarding generating function, so he has some doubt. So shall I discuss it generating functions here, or I mean, so is there anybody? So is there anybody who feels he or she is not comfortable with generating functions and maybe need a quick recap, and then maybe so we have time, and if you are free, we can like. So I've started a little bit late, and if you are free, I can like extend this. So is there, if there is anybody who is not still very comfortable with generating functions, maybe we can just quickly brush up this idea once more, and then yeah. Or I'm free to take any questions. Yeah. Hello. Hello.
Hello.
Yeah.
I have a problem that how to create that generating functions to solve that particular problem. Like in assignment 4, the question number 6, how to create that generating function.
Okay. So I won't directly solve the problem number 6, but
Exactly.
yeah. So let's just see a problem on the from this problem set. Okay.
Okay, sir.
So that would be good. Yeah. So let's just see problem number 1. Okay. x1 plus x2 plus xk is n, where each xi is an integer from n, right? So just give me a moment. Want to find number of solution of x1 plus x2 x3 equals to n. Just want to give a better solution. Just a moment. And all these xi is greater than equal to 2 and xi belongs to less than 1. Okay. So before directly jumping into generating functions, can anybody solve this problem here? Maybe try it out. This is actually a case of this balls and beans scenario, right? So does anybody remember that thing, or just try it out now and everything is fine? Yeah. So
We can just we can put 2 balls in each of these K boxes, and then like any box can have zero.
Yeah, okay, you're right. Yeah. So anybody else wants to say his or her idea? I mean, just say. I mean, you don't have to really think that it has to be right or something like that. So it doesn't have to be right. Ideas don't need to be right.
Hello.
Mm-hmm.
So one way to think is that we can design the functions like x1 square plus x square plus x cube plus x4 whole to the plus dot 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 whole to the power.
Oh, that is generating function. That is generating function. You're right. Yeah. So let's not just directly delve into generating function and just instead of solving it by generating functions, let's first try to solve using our good old tricks like these balls and beans techniques, right? So
We can subtract one from each and then apply the case that each one should be positive.
so shall we subtract one or two?
If we subtract 2 from each xi, then the case will be that any xi can have greater than or equals to 0. But if we
Zero.
subtract 1 from each, then we will have the case that each xi should be at least 1.
Yeah. I mean, they are equivalent. So actually, yeah. So you are perfectly right. So actually, the way I want to the way. So I mean, it's perfectly all right that you think it that way. So the way I actually feels very comfortable regarding thinking this is like this is first of all notice that this is a case of identical objects into distinct beings. Right? We have covered 4 cases: distinct object, distinct being, identical object, distinct being, distinct object, identical being, and identical object, identical being. So this is this case of identical object and distinct beings. And a possible way in which I feel very comfortable, actually I kind of like it. So one possible way is like, suppose we have this X, and suppose all xi's are say non-zero and all xi's are has to be integer. Yeah. So what is the total number of ways? Total number of ways is like this n. So there are n plus k minus 1 things. So basically we are adding k minus 1 bars or dividers, and there are n objects. So in total, the total number of objects plus bar is n plus k minus 1. And there are only k minus 1 dividers. So basically we have to choose dividers, how to put these dividers. So this is n plus k minus 1. This is for the case where xi is greater than equal to 0, right? Now, as someone has actually said, let me just take a new page. As someone has so let me just cover it also. So number of ways. Right? And as somebody has said, so suppose we kind of make this problem as consider slightly related version but not exact. So consider when every bean must have at least one balls, right? So in this case, this algebraic equation actually kind of becomes, so let's assume that like yi is like xi minus 1, right? So in that case, this whole thing becomes like y1 y this whole thing actually becomes like y1 plus y2 plus like yk equal to like n minus k, and we have actually made like yi is only greater than equal to 0, right? And then actually the number of solution is like you work it out and then it will be the same, right? So we'll find the number of solutions of y and then we'll just revert back to x, right? This will be like n minus 1 choose k minus 1. So this will be like n minus k minus 1, choose k minus 1, will be like this thing, right? And then you will add this thing and then it will work it out. Yeah, so just do that. Another way is to so for case when y1 equal, so let us assume here we are considering only case when these xi's are at least greater than equal to 2. So it will be like this case when suppose zi is like xi minus 2, and then basically you are summing over z1 plus z2 plus dot 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 and zk equals to say n minus 2k, and then we will work it out, right? So basically the point I want to make is like the way, because I like it, is like just assume that x1 equals to 0 and just remember this formula or work it out. I mean, everything is fine, and then we can do this kind of subtraction substitution kind of thing, and then uh, find whatever case we need, right? Is this okay? Yeah, someone suggested of this greater than equal to 1. Hello, hello, hello. Oh, some noise. Hello, hello, am I audible? Hello.
Yes, sir.
Oh, okay, okay. Sorry. Yeah. So let's just try to see how do you solve this problem using say generating function. So recall the idea of this generating function is like somehow assigning formal power series uh, to whatever problem that we are solving, and the whole game is like not with these coefficients but with these powers. Basically what we want to do is basically we want to convert the problem that we want to solve to a problem where these powers of x is actually has a correspondence with that instance that we want to solve, right? So a possible solution, another possible solution of this problem is like we are assuming that like this xi is so in this like, so it should be 0. First of all it should be 0. So here we are assuming like so basically a possible way is like suppose when we take say n equal to 1, so it is something like x to the power n kind of thing, right? So if, right, so one possible way regarding this is x1 greater than equal to 2, so it will be right, this somehow represents the case when we are taking only one element, right? One element or one object, and this somehow represents when we are taking two objects, and this somehow represents when we are taking zero object, because x to the 1 is x to the power 0, right? So if we consider this case x1 equals greater than equal to 2, so it should somehow be reminiscent of that fact, right? It should be something like x square plus x cube x to the power 4 dot dot dot. Yeah, because we are implicitly assuming this extra condition that x1 has to be xi has to be 2. So we are not actually considering the previous two terms, this 1 and x, right? Up till now, is it okay?
Yes, sir.
Yeah. So up till now it is okay. So yeah. So basically, for each xi, so it's a bad idea to use x actually. So let's just remove this thing. So let's just write y square plus y cube plus that. So for xi we are using this this thing, right?
In this case, order matters we are discussing, right?
No, I have not written the whole thing. So like it should be some sort of like that, right? Y square plus y cube plus dot dot dot. This corresponds to how many elements we are picking for x1. It should be greater than equal to 2. So we are only starting from 2, 3, 4, and so on.
To the power
Similarly,
k.
huh?
To the power k. No?
Yeah. I'm just writing down. Yeah. Y cube plus y to the power 4, and similar to this is for x2. Similarly to like for xk. This is for xk, right? So basically the whole thing would be something like y square plus y cube plus dot 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 to the power k, right? So now one thing I want to note is that how long do I need to write this? So I am writing this here, right? So I am writing this y square plus y cube plus y to the power 4, so on and so forth, right? Up to k, right? So how till what term shall I do I need to write here? Anybody?
Y to the power n.
Yeah, y to the power n, but we are assuming like yeah, y to the power n. Yeah. But every term should be at least square, right? So if you put
Yes, yes,
anything
yes.
y to the power n, it can only move beyond y to the power n, right? You can move only beyond n, right? Because we are multiplying starting from 2, right?
So y to the power n minus 2.
Y to the power n minus 2, yeah, exactly. Right? So basically it should be something like y square plus y cube and we want to find the coefficient of what was that case?
So we can directly skip the yn minus 2 term, right? We can take infinite terms and take the coefficient of y power n in this entire expression.
Yeah. That's perfectly all right. Yeah, I'm just saying. Yeah, there's no. Yeah. Yeah, actually that would be useful because we can you can then directly use like if you take this infinity. So then you can actually use this direct formula, right? This thing like 1 by 1 minus y is like 1 plus y square plus y. So if you subtract all this corresponding first two terms and then you'll get that thing, right? And it will be easy to find the coefficient. So the point I want to make is this note here. We are assigning excuse me. So the point I want to make is so the point I want to make is like for every variable xi, we are assigning a formal power series, and based upon this base condition x1 is greater than equal to 2, we are putting the terms here. And then basically you are kind of multiplying this whole thing and then you are finding whatever coefficient we need. So the whole game, so the whatever we are actually interested in is this power of this formal series. Note that the solution would be like coefficient of y to the power n. So this should be like coefficient. How many ways can y to the power n be generated? So one possible way of generating y to the power n is like it gets like say in first term it is like 2 and then second term it is like 2, and similarly whatever this there are k minus 1 terms and the last term say yk corresponding to xk would be like n minus 2k, right? this is one possible solution. Similarly for y3, y4, and so on, right? And all these possible solutions, whatever these solutions are, they actually correspond to the coefficient of this y to the power n. How many ways can we generate y to the power n from this thing, right? So like, what should be the coefficient c, and all these calculations for each of these terms, this coefficient will come up here, right? And everything will be added up, and then this coefficient c into y to the power n will be there. So we basically need to find how many ways this n can be generated, and this can be done in c ways, one for each of these cases, right? And so I just want to say two more things. So Matushek's book has probably a very nice set of these identity equations. Maybe you can look at that. And I also feel like if someone is so first of all, someone who asked this question, is this okay, or do you have any doubt?
Clear, clear. Right now, it's clear.
Okay, so just for the sake of this thing, so if it is so if you want to further clarify your ideas regarding generating function, so I think Matushek's book is excellent. I mean, first time I also learned from that book, and yeah, maybe you can have a look at that chapter over from Matushek's book. Yeah.
So can you post the book's name?
It's in the course webpage, I think. So let me just write it here. It's something like invitation to discrete mathematics
Yes, it is there in the course webpage.
by G.D. Matushek. I mean, all books by Matushek are excellent. I mean, if you read other books, and it's pretty extremely well written. Yeah, I think there is a yeah. Yeah, does anybody have any other doubt? So you can actually read it up, read the chapter on generating functions from here, and it's pretty very nice. So anybody have any other doubt?
Can you teach those topics like
Which topics?
particular solutions, characteristic equation, those topics?
Categorization is not very difficult, right? I mean, you can have a look, and then you can ask doubts, right? Categorization equation is nothing but assigning a kind of a. So let me just find a simple solution. In the meantime, are you people okay with this problem set, this functions things, problem number 7, 8, and 9? So let me just find a good example from that characteristics equation, and then yeah. So in the meantime, just see this problem 7, 8, 9 of this practice set. Yeah. So is that part? Is problem number 7, 8, 9 are okay? Hello, am I audible? Please somebody say something. Yeah, line. Hello. Hello. Okay. Hello, can you hear me?
Yes, sir.
Oh, just somebody, please. Yeah. Okay. Okay. Good. Okay. So yeah. So is problem number 789 okay? This problem number, total number of functions, total number of surjections, and total number of increasing and non-increasing functions. Are these okay? And then I'll just see one or two problems from this characterization. Yeah. So is problem number 789 okay, or shall I go over them for you? It's only 9 people are attending. Okay. Okay, no problem. Anybody? Is problem number 789 okay?
Yes, sir. So can I discuss the ninth one once?
Yeah. So 9 on. Is there? Shall I discuss anything more, or hello? Or other problems are okay?
The other one is onto function. We have to use inclusion exclusion, and
Yeah. Yeah. Please include. So regarding problem number 9, we'll just see this here. So we have two sets, right? Two sets of K2. Yeah. Right. So basically, you want to find the total number of increasing and non-increasing functions, right? So let's just first see the easy case. So just first find this number of increasing functions. So so basically, what is an increasing function?
so we need to consider strictly increasing in
Yeah. So if it is nothing, otherwise, what does mean non-increasing, right? I mean, non-increasing is not strictly increasing. Right? So basically, what does this mean? So if x is less than y, so fx needs to be less than fy, right? So suppose we have this k elements here, and we have this n elements here, right? So the idea is like, suppose I have fixed 2, right? Suppose it is going to, suppose this is 2 and this is going to 3. So for 1, I can only map 1 to 1 or 2, right? Because otherwise I will violate it, right? Is this okay? So I can only
Yes, sir.
map 1 to 1 and 2, right? Because otherwise it will violate, right? So let's just go a little bit opposite way. So how many ways can I find, can I actually map k? So there are n possibilities for k, right? Right. So once I have fixed a particular k, right, how many are remaining on this codomain? There are n minus 1 remaining, right, for this k minus 1. So total number of ways should be like, so the point I want to make is like, once I fix the value of a higher number, the possible number of solutions of the suppose I fix k to be mapped to n, right? Say suppose I fix k to be mapped to 2, right? Then from all to 1 to k minus 1 can only be mapped to 1, right? So once I fix where the larger values are being pointed or mapped, the smallers are kind of the solution space of the smaller numbers are kind of being reduced, Is this okay?
This case is valid because 1, 2, k
No, no,
minus
this
1 are
case is
mapped to
valid.
1.
This case is perfectly valid. The point I want to make is like once I fix this higher number of domain, the total number of solution space of 1 to k minus 1 is decreased. So suppose in the very beginning, 1 to k minus 1 can be mapped to anything, right? Other than n.
In this case, it is 1 to k minus 1 are getting mapped to 1.
1.
So
So the point I just want to make is like total number of solution space of mapping 1 to k minus 1 is much reduced. It's only 1. So once I fix the higher values where I want to put the higher values of domain, they kind of reduce the total number of ways, how many ways I can actually point the other values, right? So once I fix,
but in this case, it is not increasing function, right?
no, this is a stupid example. I mean, yeah, this is not an so I should have write or something like that. So suppose k maps to k, right? Yeah, that's not correct. Yeah, thank you. Yeah, so yeah. So the point I want to make is like once I fix where the larger values are being pointed, the total number of possible solutions of the other numbers are kind of getting reduced, right? So once I fix k, I can only put 1 to k minus 1 to up to first k minus 1, right? Otherwise, increasing property would not hold, right?
Yes, sir.
So this is a kind of the main crucial idea. So what happens when so we'll just some sort of go backwards. So how many ways can we map k? So there are n possibilities, right? So how many ways can I now? So once I fix k somewhere, right? Suppose what will be the best case? K is mapped to n, right? So there are n minus 1 choices remaining, right? So what? So then we can actually map k minus 1 to n minus 1 places. Similarly, k minus 2 would be n minus 2. Similarly, this should be like n minus k plus 1 choice, and this should be something like n factorial by n minus k factorial. Is this okay? Hello? Hello?
Yes, sir.
So now can you just for a moment think of this non-increasing case? Just directly before jumping to the solution myself, just can you just have a little bit of thought? I mean, x less than y, then imply fx can be less than equal to fy. Anybody?
So in this case, the previous one, the increasing case,
Yeah.
so that is basically NPK, right?
Yeah, exactly. Yeah.
But NPK in NPK, we are arranging we are considering all possible permutations of the subset of k elements from the set of n elements.
Yes.
So, but given a subset k from the set of n elements, we will only have one increasing sequence, right?
I don't understand. So first element can be choose like n ways, right? First element can be choose n ways. There are lots of choices, right? Given the first choice, there are n minus 1 remaining choices to be made, right?
Yes, the first element can be chosen in any n ways, but given the first element is chosen, the second element will not have n minus 1 choices because it is a strictly increasing sequence. So it will have only those choices which are more than the first choice.
No, we are going backwards, right? We are first mapping the larger values. Right? Because we somehow need this thing, right? We somehow need like f1 has to be less than f2 less than f3 less than
Yes,
f.
sir. So if we go in the backward direction, Fn will be mapped to the largest value, right? Among F1 to Fn.
Yeah,
So it will not have n choices. So we choose a subset of k, it will have only one choice.
yeah. Okay. Don't follow. No, this is strictly increasing case, right?
Yes, in the strictly increasing case, let us suppose choose a subset of k elements from the set of n elements.
Yeah.
And given a set of k elements, we will have only one increasing sequence.
Right.
So it
Right.
will be n choose k.
Right. But that would give this. Maybe I'm missing something. I'll just mail you, right? So maybe I'm missing something. Am I missing something?
Like, so let us suppose we choose a subset of k elements from the codomain of n elements.
Yeah. Then we'll just
So
point it accordingly, right?
yes, then we will have only one possible permutation because the elements are strictly increasing.
Yeah. I think you're right. Yeah. I'm missing something. I don't know. I'll just post it over the classroom. Okay. Just missing
Okay.
something. Sorry about that. Yeah. Maybe I'm just missing something. Yeah. I'll just post it by tonight. Uh, yeah. So I just want to say a couple of things of this characteristic equation. So characteristic equations are kind of like so we just generally solve like this case, which is like linear and homogeneous. So it will be like something like an is like c1 an minus 1 plus c2 an minus 2 dot say ck a of n minus k, right? And this is homogeneous because there is no term other than a, so there is no some constant or something, right? Say a n or n square, there is no constant or like that, right? Now let us treat let us assume that an is like some alpha 1 to the power r1 to the power n and alpha 2 r to the power n, right? And so if we plug it here and solve, suppose r1 not equals to r2, right? So there are two distinct roots of this equation, and then the total number of solutions would be like so the type of the solution would be something like this, right? So the point I want to make is like, so let's just see an example and that will be clear instead of formally. Suppose I want to solve this, right? And suppose I assume like an is say r to the power n, right? So what happens if we put this? So r to the power n is like equal to r to the power n minus 1 plus 2 into r to the power n minus 2. So if you cancel out r to the power n minus 2 from both sides, so it will be something equation of this sort. So it will be something like r square minus r minus 2 equal to 0. It has two solutions, distinct solution, 2 and minus 1. So using this formula, we can actually get a solution like an is like some constant alpha 1 to the power n plus some constant alpha 2 to the power minus 1 to the power n. And obviously there will be some sort of base conditions given. So a2 equal to say 2 and say a1 equal to 7, and then using these base conditions you can find actually alpha 1 and alpha 2, right? So this is the case when the two roots are distinct, right? R1 not equals to R2. Right? Now what happens when R1 equals to R2? In that case, the solution would be some form of like this. An should be alpha 1 R1 to the power n plus alpha 2 n into R1 to the power n. So suppose like this is the solution, like an equals to like 6 an minus 1 plus minus say 9 an minus. So if you solve this, say assuming an equal to the power n, basically it comes sort of so r1 equals to like 3, and then say an equals to some alpha 1 to the power 3n plus alpha 2 n into 3 to the power n, and using whatever base conditions you have, you can actually solve this. So this is case when there is a single root, right? This is the case when r1 equals to r2. And this is the case when r1 not equals to. It's also another case where there are say n solutions. Say like in that case, so r1, r2, rn, and all ri, rj are not same. In that case, the solution would be something like an equal to alpha 1 r1 to the power n alpha 2 r2 to the power n. Something like that. I mean, yeah.
Okay, sir. So one thing, in the solution, if in the assignment or exam, if the recurrence falls in any of these cases, can we use the homogeneous method, like this method directly?
You can actually guess that, but you have to prove it using induction. There should be a formal proof. Right? This is some sort of a verifying thing, kind of to consider. But it should be a proof, should be of a induction kind of thing.
And if we use the Master's theorem, do we need to prove the Master's theorem?
No, of course not. Master's theorem. No, but you can only use Master's theorem to verify your solution. You cannot not directly write like using Master's theorem, I'll get this solution. You cannot do that.
Like while guessing the solution, if you use Master's theorem,
Guessing is fine. By any means you can guess. That doesn't matter. But you can use Master's theorem, Chakravarti theorem, whatever theorem you want. You can use linear homogeneous solution, whatever way you want to solve it. But whatever way you want to guess it, but you have to prove the solution using induction. I mean, yeah, guessing can be done in any way, but as I'm speaking said before as well, so Master's theorem as well as these techniques are not formal proofs. These are for your guessing purpose, but you have to prove it induction, because once you have some sort of guess the solution, it's just a 10 minutes calculation, maybe 10, not even 10 minutes, 5 minutes writing, right? That would not be very difficult.
So like the Fibonacci recurrence relation we have,
Yeah.
we can solve using this homogeneous equation method, and then we have to prove it by induction.
Yeah, that's a possible solution. Yeah. But I think solving Fibonacci equations via generating function has itself it's pretty beautiful, because there are a couple of problems that are kind of very tricky to solve by these things. Yeah, Saurabh has covered that proof, right?
Yes, sir, as covered by generating functions.
Yeah, yeah.
Like, can we do this the Fibonacci or in
So basically,
any other?
you won't be asked in the exam to do this Fibonacci thing. So it will be something of a different sort. I mean, you won't
Like,
get
if it falls in the category of homogeneous equations, can we take the help of homogeneous equations and
yeah,
solve?
you can guess by any way. It doesn't matter. These are just
Even if it
learning.
is guessed by generating functions or linear homogeneous equation method, we have to ultimately prove it by induction.
Yeah, yeah. And
Okay.
the reason being of covering generating function is like there are a couple of cases where it's pretty hard to come up with a corresponding solution other than generating function. So say for example this coin problem, this problem 6 number of this, it's pretty hard to come up with any solution other than generating function. So yeah, so so it's worthwhile to learn that technique.
So in the problem 6, after we have come up with the solution with generating functions, we have to prove that by induction.
No, if you solve it by generating function, yeah, that is okay. I mean, you can also prove that for completeness. Yeah. But using Master's theorem and this linear homogenization equation, these are not formal solutions.
If we use these two techniques, then we have to prove it by induction.
Yeah, yeah. So if anybody has if nobody has any other doubts, then probably we'll stop. Probably I'm a bit over time. So do you have a class after that? Do you have a class after this?
This is today's Sunday, so mostly no class.
Oh, okay. So yeah, okay. Okay, good. So great. So solve the other problems of practice set, and if you have any doubts, maybe we can schedule another tutorial sometime and try to submit problem assignment 4 as soon as possible. And again, if you have any doubt regarding that, I mean, feel free to mail us, and you can ask Saurabh as well in this class.
One question.
Yeah.
Say in this generating function only.
Yeah.
Say we have created a generating function.
Okay.
Now what? Now we have to solve that function.
No. So
Yes.
yeah. So so the idea of this generating function is like very cleverly using these powers of this formal power series, like
yes,
we are basically given a problem instance, we are basically somehow converting that problem instance into a power series thing, and where the powers are basically representing the corresponding numbers in that problem instance. So suppose so let's just go back a little bit and let's just see one thing that we have done. So let's just see this problem. Number of solutions of this greater than equal to 2, x1 plus x2 plus xk equal to n, right? And where xi are greater than equal to 2 and xi are natural number. So basically the problem here is to find the number of solutions to regarding this solution, right? This equation.
Yes.
Right? So
yes.
So very well we can solve it by this way or write a generating function of this sort. But basically at the end of the day we want to find actually the number of solutions, right? Number of solutions of that equation.
So what I was telling, like in case k is very large, then even this function, I mean finding coefficient is also tough.
No. So during exams that won't be the case. There is no point of so we are not actually trying to give you like very calculative stuff. So that's not the goal. That's not the goal, right? I mean, this is just a pure brute force calculation. That's not at all the goal of the course. But yeah, there is some calculation involved. So if you want to solve in real life, there will be a sort of calculation. But that's not the main goal of this course. I mean, doing big calculations. That's not at all the goal of this.
Say, for example, assignment 5, problem number 8. It will be
Assignment
like
5,
one.
there is no assignment 5, no?
No, assignment 4 means the recent assignment.
Yeah, assignment number 4, this problem number 6. Right?
Last problem, yes.
Problem number 6, yeah.
There we have to somehow produce a generating function where the highest power we have to find is for x to the power 50.
And
So
the base
that
case
will
is at
be,
least 1. I mean, the start would,
yes.
yeah.
So that will be again lot of calculation.
Yeah, but I mean, it's a assignment, right? And you can try it out, right? I understand your problem, but yeah, you can try it out, right? I mean, it's better to somehow, at least once in a while, solve, like, but that won't be the case in exam. I mean, that's for certain.
Okay, fine.
Yeah. So if anybody has no more doubt, then maybe we'll stop. And if you have further doubts, feel free to mail us. Okay. See you. Yeah. Okay. Okay. So I'm just ending this meeting. Okay. Is this okay? Or do you have any other doubt? Hello. Hello. Do you have any other doubt, or otherwise I'm ending this.
No, sir. It's
Yeah.
okay.
Okay. Okay. So I'm just saying. So if you have any other doubts, so feel free to mail us. Yeah.
Okay, sir. See you.
Yeah.